Okay, I'm Pietro. I'm a PhD student here in MP, and I do work often directly on X-ray data, on the spectra and on the light curves, as I work with transient phenomena and also understanding the spectral shape of this transient phenomena. And today I will tell you how to actually do what Jofi was describing. So going from wanting to study a source all the way to having light curves, spectra, and images for this type of source. So I would have loved to make this tutorial very interactive, the same way that I did for the eROSITA data analysis school, which happened in October or maybe November, but anyway, in 2024. But unfortunately, for X-ray spectral extraction and analysis, you need a lot of software, which is not so trivial to install. Here's a list of the main software you will need. So we have DS9, for example, which is a visualizer tool to work on FITS files, FITS images. You can draw regions. I will show you in a little bit how this is done. And then you need specific software to process the eROSITA file, which in this case is ESAS. Sorry for the ambulance. Then these two softwares I didn't highlight because they can be optional in case you want to work with already extracted products. So the eROSITA team already extracts light curve spectra and everything you need to do your analysis for sources which are relatively bright. So not most, but many sources that you will work with eROSITA already have spectra and light curves extracted, so you don't need to visualize anything or to process anything. What you will need for the analysis, though, is the general HEASoft package, which includes XSpec, the software that Jofi was just describing, so that you can actually do the spectral analysis. However, not all sources have products already extracted because there are many, many sources which are indeed detected by eROSITA. They are present in the catalogs, but they don't have a detection likelihood so high that the pipeline decided to extract the products for them. So this is something you will have to do yourself. Okay, but let me show you how we actually do this extraction. So first of all, this is a source that Jofi was describing. This brightest quasar at redshift below 1, very bright source. I opened it on Simbad so that I could get the coordinates for the source, and here is what it looks like in 2MASS, for example. So how do we go from coordinates to actually getting data for this source? Well, you have to go to the eROSITA page, of course. So here we are in DR1 page. So the overall eROSITA page looks like this. And you can go to data releases, DR1, which is data for the first of the eROSITA All-Sky surveys. And on this page, you have a lot of information. Maybe I can expand a little bit on what Andrea started to say so that I can cover also that part. But okay, you can have your home describing a little bit what the DR1 is. You have a tab with data, something on data analysis. So this is where you will find everything about ESAS, the software to analyze the data. So how to install it, what the tasks are, a cookbook with some recipes to do some type of extraction and data processing. But then you can also find more tabs regarding technical details, known issues, and many, many more things. But of course, in this case, we're more interested in the DR1 data. So this tab also contains lots of information. It contains what Jofi was saying earlier. So the attitude files, which describe the orbit and attitude files together, they describe the pointing over time for the telescope. So if you want to know if which part of the sky was observed in which time, you can use these files, or also for simulations. If you want to simulate X-ray data, you are going to need the attitude files of eROSITA. Something else that you can get that I think is really, really useful is these upper limits. There is an upper limit server which was developed by Dusan Tubin, for which you can derive upper limits for a single position. So you just put the name of your object or the coordinates, and then you submit and you get an X-ray upper limit, but also for multiple positions. So you can input a list of targets, and even if they're not detected in eROSITA, you will always have an upper limit on the flux. And this is very important because, as Jofi was mentioning, eROSITA has provided the deepest all-sky survey of the sky. So this means that the deepest X-ray upper limits will be provided by eROSITA. And what's also nice is that if the source is actually detected, you will be told by this upper limit server. So it will say, okay, but there is a source 1 arcsecond away from your position. Maybe this is actually your source, and you don't need to get an upper limit, but you can actually get the proper flux. So something else which is present in this DR1 data is overall the eROSITA archive. So this is where all of your data will be. You can also get just maps and the source catalogs, which I guess is important to look at the catalogs to understand if your sources, which are maybe detected in the optical, also have an X-ray counterpart. But for our purpose, we will go directly into the eROSITA archive because we already know that our source was detected in the X-rays, as Jofi published a paper about. All right, so when you're here, there are many ways that you can access your data. For example, you can do the sky view, which will show you the whole eROSITA sky. And you can play with it, you can move it around, and you can see that the sky is tiled into what they are actually called sky tiles. So this are tiles which I can't remember exactly the size, but I think they're like 1 degree by 1 degree, maybe, I'm not sure, where you will have all of your sources. And you can find, I hope you can see, maybe it's a bit small, but in all of these sky tiles, you will have a center tile position. So you will have an identifier for this tile with the position of the tile and all the sources that are detected. So if you click on one, at the bottom, you will receive some basic information, such as the coordinates, a link actually to the source products, and then you will receive information on the rate, on the counts, and on the detection likelihood, and also on the extension likelihood. So, for example, the source I just clicked on is a point source, and I think this is clear. And what you're seeing now is the RGB image of eROSITA in which different bands, so soft band, medium band, and hard band, are plotted into different colors. This is not the only way you can visualize this. You can also change here on the right what you're seeing. So you can only see the rate in band 1, which in this case is 0.2 to 0.6. You can see maybe in the hard band, right? 1 to 2 kV, harder band, what this looks like. So you can explore in a visual way what the sky looks like. And you can also plot different catalogs. So you can also add sources coming from ROSAT, which means that you have both data from the 90s and data from nowadays. So let's look for data for the quasar in question. So I just get the coordinates here. And I can put them, I can input them. I can even just put the name of the source. I think I can try to do this. And the website is able to resolve sources which are on Simbad or NED, so you don't even need to actually know the coordinates. Let's see if this works. Yes, it did. So indeed, this is a bright quasar. You can see that it also has a kind of a bright detection. And if you zoom in closely, you can see that there is a catalog source. And indeed, the detection is quite significant. So you have a high detection likelihood, and it tells you that you have almost 600 photons, which is really, really a lot for X-ray data. Okay, so what you can do already by having this is that you click on this link for the source, and you have even more visualizers. So on the top left, you have the same thing that you were looking before, but on the right, you have data from Allwise. So you can see what the infrared looks like. On the bottom, you have DSS2, and on the bottom right, you have eROSITA, but just the soft band. So you can already understand if maybe, okay, I think this is also nice to visualize how different the PSF of X-ray data compared to other wavelengths is, because you can see that there's a very large blob, and here we have a lot of optical sources which could have contributed to this emission. And from here already, you can see at the top that you can do this add to basket. So you add your source product to your basket. You can go to your basket, and already you have source products for your source in question. And if you do download, let me go to the folder that I want to work in. Okay. This download is very quick. And if I show you my folder where I downloaded it, I can extract it. And inside these many nested folders, I extract something else. And here I have all of my products. So technically, you're already ready to do your spectral analysis, light curve analysis, anything you want to do. let me explain a little bit what we're seeing though, because this is many, many files and maybe you wouldn't expect to have so many files. So basically you have these files which are named by telling you the name of the eROSITA All-Sky survey, so 01, because DR1 is only the first of the 4 eROSITA All-Sky surveys, 4.5 actually. And then you have an identifier of the sky tile in which the source is found. And then a number, which is 020, then it becomes 120, 220, 320, all the way to 920, which I will explain in a second, and then what the actual products are. So in this case, the products contain the ARF, so this basically response matrix that Jofi just introduced to you, the background spectrum, so a well-sampled spectrum of the background representative of the background that's contaminating the source, the light curve, so already you can analyze the light curve, the RMF, which is the conversion from energy channel to actual energy, which you need to do spectral analysis, and I guess what most people are interested in, which is the source spectrum. The reason why you have 9 or actually 10 sets of these files is that you can choose, or you can choose to extract products not for all of the 7 eROSITA telescopes, but only for a selection of them. So 020 is the most complete data sets, which includes all of the telescopes. But then 120, 220, 320, respectively, mean only using the telescope 1, only using telescope 2, only using telescope 3. There could be reasons why you would want to choose only some of the telescopes. And you will notice that there is also 820 and 920, which there's not 8 and 9 telescopes. So it means something else. In this case, 820 is basically all telescopes except for 7 and 5. If I'm not mistaken, these are the two ones that should be excluded, which are affected by some light leaks issues. So in some cases, you might want to only restrict yourself to all the other telescopes which don't have these issues. And 920, I actually am not fully sure. I'm not really sure what this is, but we usually don't use it. But this is documented, so we can find out what the 920 processing is. Okay, so one could say, I have my bright source, I have my products, I can already start analyzing this data. However, this is the case for this quasar, which is quite bright, but not all the time you will have products already extracted. So what I would suggest to do instead is to look for the sky tile search, in which you put the name of the source. You can resolve the coordinates of the source going through Simbad or NED, and then you can look in which sky tile the source is located. And so you can actually process the event files yourself. So in this case, it's looking for sky tiles which are within a radius of 2 degrees from the source position. This is a bit of an overkill. Our source is a point-like source, so we don't really care what sky tile this is, but in some cases, maybe your source is extended, your source might be closer to the edge of 2 sky tiles. And so maybe you want to download events from 2 sky tiles, combine them, and then process them. This is not our case. And here it tells you all the sky tiles which are connected to this source or within this distance. And it tells you the distance in Ryan-Deck, the sky tile number, and then it also tells you if your source is within the range of the sky tile. Also, it will tell you whether the sky tile is owned by MPE or if it's part of the Russian sky through which you don't have access. So all of the sky tiles are not available to us, of course. All right, so we have identified that this is the sky tile in question. I think you can also see from the products I extracted before, that the files contain indeed 176, 132, and it is indeed the same number of this 176, 176, 132. And here you can download directly the event list. So the most complete process data set you can have. So events contain all the information about position on the detector of the events, so the photons, the timing, and the energy. So this is what you want to do to extract light curve spectra and images. And so you can just click on it and you will get your events. And it's, again, quite fast. I mean, these are large, but still very fast. And And what you also want to do to visualize your data is usually to produce an image. You can do this. And in fact, here in the slides that will be available for you, I wrote how you're supposed to create an image. You're going to do this with the ESA software, okay? And in the ESA software, you have this task called EV-Tool. Here's the page about it. So if you go to data analysis, tasks, you can find a list of all the tasks and what they do. And for event manipulation, you only have EV-Tool. It's nice. It's very simple to use in order to create an image. And so in this case, I wrote here quickly, you just say the name of your event file you want to create an image from. You want an image? Yes. What's the name of the out file? Was just a test image. And then the energy range through which you want to create an image. In this case, I chose the main eROSITA band. But yeah, we can run that, or we can just download the soft fits image, which is the image produced in the same band. And so I'm going to do it. All right, so now you have everything you need to do your spectral extraction and analysis. So let's go back to the folder where I just downloaded this file. The first thing you want to do is to actually open the image and see what your source looks like. So we do this with DS9, if DS9 works. All right, so unfortunately, we don't have a lot of photons, so X-ray images never look that nice. And indeed, when you open it in DS9, all you see is usually just black. Let me zoom out so we can actually see the whole image. All right. Yeah, so already here you don't see really anything, but something you can do in DS9 is to change the scale of the contrast. So instead of having a linear scale, maybe you want to go into log scale. And already some events are starting to pop out. So you can see that in some regions, we have clumps of photons. These are definitely sources, but still, this is not very nice to visualize. So something you can do, again, in the scale, is to make so that the contrast is defined by the 99th percentiles of the distribution of photon counts. But this is, I mean, you can play with these numbers. It doesn't really matter. And then on the S9, if you hold your right cursor and drag along the image, you can kind of play with the contrast. You can see that the color bar is changing with my mouse as I'm holding the right click. But again, we have not so many photons overall, so something else you want to do to have prettier images is to maybe convolve the image with your favorite smoothing kernel. And this you can do by going to Analysis and then clicking Smooth. It's going to take a little bit. Okay, did it. You can also do it from this tab here. You just smooth your image, and already you can see that the image is starting to look a little bit nicer. So you can play with the contrast again to remove some of the background. All right, and this is already looking a little bit more like an image rather than just a collection of events. You can adjust your smoothing parameters. So for example, you can change function. Maybe you can use a top hat function or an elliptical Gaussian. Or you just want to keep a Gaussian kernel for smoothing and maybe make it a little bit larger so that you smooth even more. And let's see what it looks like. Right. So when I do this, these events here are looking much more coherent, I would say. Again, you can play with the color maps. Maybe you want to choose you can go to color and choose your favorite color map to have something which looks nicer. And maybe this is the best way you want to visualize your data. Okay, these are just cosmetic things. You don't really need to do it. And actually, maybe for proper analysis, smoothing can mislead you into whether sources are really there or not, because you are maybe putting together photons which are just stochastic background photons. But I think it's always nice to see. So as I was saying before, these skytiles are quite large. So we want to identify where our source is. I mean, if we remember from the skytile search that we were doing before, our source is around this location, and I think I already see it. Also, I've already tested on this skytile, so I know where the source is. But I guess the best way to do it is to go and create a region and input the coordinates of the source. So in order to do this, you go into Edit and select Region. You can also do it from this menu here. And then if you drag along the screen, you're creating a circular region. If you double click on it, you will see that you open the coordinates for this source. And so let me get the coordinates from the website. So, all right, since I had resolved it, let me just copy and paste them into my region circle. So I changed my my degree system to go into my coordinate system to go into degrees, and I just input the coordinates for my source should be. All right, and then I open again the S9, and indeed, this is where my source is located. So, okay, now this region we're going to actually use to extract the spectrum. So what we want to do is to define an appropriate radius. So in this case, I change this to arc seconds because I'm more familiar with it than fractions of degrees. And of course, a radius of 400 arc seconds doesn't make any sense. It's much larger than the PSF of eROSITA, and the source is, the source is just located in the center. So what you want to do is that you can either use a number which is defined by maybe the half energy width of eROSITA, but then you can see that this region is, it is the half energy width, so you're losing half of the photons. So what you can do is two things. You can either adjust it by hand and decide when you are satisfied with your source extraction region, or you can play with numbers based on, some of this PSF, basically the encircled energy fraction or the PSF of the instrument is reported on the eROSITA website, so you can choose numbers based on that. I think for this source, I would like to go with an extraction radius of about 70 arc seconds, maybe. And if I unsmooth my image, I can see that most of my photons are stored indeed within this 70 arc second radius. So once I selected my region, I can just go to region again and then save it. So I'm going to save it as my source region. And here you can choose the format. It doesn't really matter. It's more up to you what you choose. For source tool though, which is the tool you use to extract source products in eROSITA, you usually, maybe David can also say what he thinks about it, but I like to use the Chow format, which is more compatible. And also I don't want to save the coordinate system in physical, so in pixels, but I want to save it in RandDec. So I go into word coordinate system. And then for FK5 is fine. For X-ray data, the differences don't really matter. We have not such a precise position anyway. Okay, so I just save it. All right, so I have my source region, but again, you need to also model the background. So I smooth again. And for my background selection, I want to choose a region which is sampling. I could just draw a circle here, right? But this would, if the background is maybe varying and in a non-uniform way over the whole image, maybe I'm biased towards a region with higher background or with lower background. So ideally what you want to do is to choose a circular region around the source. Ideally you want to choose the background which is actually behind the source, but that's impossible. So you just choose to sample the surroundings of the source. And you can do this by going into region, selecting a different shape. You can have multiple shapes that you can choose. In this case, I'm looking for an annulus. So I draw an annulus on my screen, and I can adjust in more detail the parameters. But I guess for the scope of this tutorial, I don't know. I could say, okay, I want the outer radius to be very large, so I make it like this. It doesn't really matter for this tutorial, so I will not do it. And also, we have potentially several contaminating sources which within our background extraction region. So I can definitely see one here and one here, and maybe some more things happening at the edge. So what you want to do is to exclude them. I do think that it's always important to unsmooth when you do this thing, because, for example, let me smooth again. So this thing here at the top looks like a source, but if I unsmooth it and I look at the events here, I'm not so sure that this is an actual source. What one should do is to go through the catalog and actually look at where sources are detected and remove them. But for the purpose of this tutorial, I'm just going to consider these and this source as contaminating into my background. So what I want to do is to go back to circular region and to mask them out. So I go to circle, I draw a circle, and I go into property and say exclude. So now the circle is barred with a red bar. So it means that I'm excluding this source. I can put it on top of my source like this. And now this source will not be included in my background. I'm going to put it for this one too. So again, property exclude. All right. And then once I'm done with this, I go to region and select them all. I could have done Control A. So all of these are selected, and I create a composite region. So I go to region, composite, create. So now this one is all one single region. And now I can save this. So again, save selected regions. Wait, first I have to select actually. Okay, region, save selected regions, and this one will be my background region. So background again. And so let's look at what these regions look like. So for the source, yeah, it's a circle with coordinates and then with a radius. And then for the background, you can see it's very nice. You have annulus and then minus circle, minus circle. So you're excluding sources. I saw a question, so maybe I will answer now. How is the radius of the central source and surrounding sources defined? So the radius of the central source, I think you mean in the source extraction, not the background extraction. You can either look at the encircled energy fraction distribution, so the PSF shape that Andrea showed you at the beginning, and you can say, okay, I want to collect 80% of my photons, which should be produced within 80% of my, which will be within this radius, which you can find. It should be like 45 arc seconds in radius. But this, if you're doing this by hand, it's also a little bit up to you. So brighter sources, you can extend way more out, because if a source is brighter, these remaining 20% of the photons, which are outside of your 45 arc second radius, are still much more than the background. For a faint source, instead, you might want to restrain yourself to 50% of the, no, maybe 50 is a bit less, but like to a lower percentage of the PSF, basically, so that you are ensuring that the source you're extracting has a good enough contrast with the background. While for the background region, what you should do ideally is to extract the largest possible background region and then remove all the contaminant sources. So the products that are produced by the eROSITA pipeline contain already pre-selected background regions, which are huge annuli regions in which all the sources detected in the eROSITA catalogs are masked out. I couldn't do this right here because I would have to look at the catalogs and everything. There is also a way to do this automatically within the source tool task, which I'm about to show you to how to extract spectra. But it's a bit more complicated. So if you want to actually do this later on, you can get in touch and I can show you how to do it. So basically automatically masking sources out. But I thought it would be interesting to show what the actual process would be. But I will finish and then we can go back to this. All right. So now that I have my source and background region, all I have to do is use ESAS again to extract my products. And here in the slides, I have written the code that I need to use, and let me show you how to actually use it. So I don't want TS9 anymore. Okay. Just 1 second. Okay. So I have to initialize both Airsoft and ESAS, and then go into my favorite conda environment. And then this is the code. So the code, again, you can find many information if you go to the source tool page of the ESAS tasks. And it does a lot of things. This is a bit more complicated, but basically it goes from event files with a source to spectrum, RMF, ARF, light curves. So everything basically. And in this case, we have a bit more parameters than for the image. So let's go through them. The first thing you have to do is to, of course, input your event file that you want to analyze. And my computer is slightly freezing, but I think we can do this. So the events, not the image. The image is just for identifying where the source is. And you do this. And then you want to tell the coordinates of the source, which I should get again from the website. So just quickly. Okay, and then you just want to give a prefix which tells you what name the output files should have. So in this case, just products, I don't know. And then to do, which contains all of the things you want source tool to actually do. So you have spectrum, RF, RMF, and then light curve. But what's more important than light curve is LC core. So basically, because of the scanning strategy of eROSITA, the light curve will be produced by the source with the telescope going through the source. So it means that at the beginning of the light curve, the source will be more off axis, and at the end of the light curve, the source will be again more off axis, while the maximum on axis is obtained at the center of the light curve. This means that we will have strong vignetting affecting our measure counts. So what you want to do is to correct for this effect by creating this corrected light curve so that your rates are corrected for the fact that you are not always on axis as you observe the source. Then you want to tell which telescopes you want to extract. In this case, it's all of them. You tell the regions, so source region, background region. It's a point source, so I want a point-like extraction. And then some parameters for the light curve, such as, okay, this is not really important, but I just want a regular extraction. I want to extract 10 seconds means, and I want to extract two light curves, one in the 0.2 to 2.3 range and one in the 2.3 to 5 kV range. Then I want to choose the PSF. Flag select is something a bit tricky, also not always obvious to understand. I can show you on the website, but it's basically a way to filter out bad pixels or events which are not should not be extracted. And you can go on this page and it will tell you what all of these different numbers mean, which type of patterns are chosen. But 8 overall is a good number. It's a bit, yeah, this is a bit more tricky. And then these other things are not really important. You just want to say write instrument 0. So if I do run this, you can see that it's running quite fast. And it's done. So now if I go back to my folder, you can see that I have my ARF, my background spectrum, my light curve, my RMF, and my source spectrum. So I can already start analyzing my data. And within the Hairsoft, you can do this very interactively with the XSpec package. So let me open XSpec. This is an X-ray spectral analysis tool, which is really, really easy to use. So, I mean, once you know how to use it, but overall it's very simple and interactive. So you can say, okay, XSpec, my data is this product's source spec. So this is where the most exciting part starts, in which you load data in XSpec. And XSpec is very user-friendly, I would say. So you can quickly open a command prompt. Oh, sorry, that's not how you do it. A graphical window, and you can already visualize your data. So you just do plot logarithmic data, and you can already see your spectrum here. This is not very nice because it's also in channel, not in energy. So you move to set plot energy, then you can plot again, and now you're seeing your spectrum in a KV. On the x-axis and on the y-axis, you have counts per second, and you can rebeam this just for visualization purposes, and already you have your very nice spectrum, which is ready to be modeled. You can also show the background, so set plot back, and you can see that our source is well above the background. You wouldn't fit it down to 0.1 kV, so maybe you would ignore everything up to 0.2 kV and everything above 8 kV. You can do it like this. You plot it again, and then you want to fit it, so you just say model power law, for example. And then you just say, so this is an unbin spectrum. The rebinning is only visual, so you cannot use chi-square statistics, but you want to go into cache statistics. So you just say statistics chi-stat. So this Poissonian statistics, and you can say fit it. And once you do this, you can see that I plot it again, and you can already see the power law. And you can already derive an estimation of your photon index, which is 1.4, which is very shallow for an AGN. So maybe we are missing something that's actually absorbing the true emission. You can do all sorts of analysis. You can make contour plots really fast of your parameter distribution. I think I shouldn't do this because David will show this. So just to let you understand, this is how X-ray analysis has been done for a very, very long time. Now we're moving into a bit more sophisticated methods by using a Bayesian approach, but this is also fine. Technically, you should rebin your spectrum before you do this, but you can already derive physical parameters from doing this. All right, and just for completeness with light curves, let me just close this terminal. For light curves, these events are a bit tricky. So what you want to do is to use this very nice software, which was developed by Ricardo Arcodia, who was a member of our group, member of eROSITA for a very long time. This eRebin code is very simple to run. Well, the link is in my slides when I will share the slides. But basically, I already downloaded it. It's called Rebin eROSITA Pi. And if you, 1 second, I go into my correct environment. If you, sorry, activate. So, and if you just run this code, Rebin eROSITA, you say where you want to run it. Let me just check the actual syntax. So indir here, names, you just say the name of the file. So products, light curve, it should be good. No, I forgot to put the out there. Okay, so this is already plotting my light curve rebin to the eROSITA. So the eROSITA scanning strategy is such that a source is observed for 1 day in EROS1 every 4 hours because it's the rotation period of the orbit with a 40-second scan. So you can get a light curve which is about 1 day for EROS1. Of course, if you had access to EROS2, 3, and 4, you would get 1 day light curve 6 months after a 1 day light curve and all. And the thing that this code does is basically produce light curves beamed to this 40-second scan. And indeed, by running the script, I quickly produced this folder with images. And here you can see what the light curve in the 0.2 to 2.3 keV band looks like. Doesn't seem to be very variable on these timescales. And you can also see what the other band that I chose, which was 2.3 to 5 keV band, what it looks like as well. And of course, we have less counts in the harder band because eROSITA is less sensitive to it. These are just images where you can easily adapt the script to just print the output out if you want to do some numeric analysis of this. And with this, I will conclude basically. So in the slides that you will have, we have plenty of links with all of the codes that I'm using. I personally prefer to use Sherpa compared to XSpec for analysis because it's more Python friendly, but this doesn't really matter right now. And what I just want to say is that the overall region selection and analysis is common to all of the X-ray facilities. So if you work with XMM Newton, Chandra, you're doing the same things in DS9, and you're also going to need Hailsoft to analyze your data. But each of your instruments will have a specific pipeline for processing the data. So for extracting spectrum with XMM, you would need a specific software. If you want to do it with Chandra, you will need another specific software. There are some softwares which are kind of versatile, so they can do data extraction for most surveys. This one is called XSelect in particular, but overall, it's quite specific what you're going to do. And with this, I leave you so that David can show you how to actually in detail do spectral fitting and spectral analysis. Although I'm an AGN person, so I extracted this AGN. David will instead work on an X-ray binary spectrum, but the concepts are the same. It's going to be a different spectrum, though. And if you have quick questions, I think you can ask them now. Otherwise, later in the Q&A session. I will stop sharing, though.